Okay, good afternoon, everyone. Thank you very much for joining us for today's UWEcyber seminar. We're delighted to welcome Justin Hart from Ribbon Communications. So Justin's going to be talking to us today about evolving complexities of securing telecommunications infrastructure in the 5G era. So Justin Hart is the Chief Technology Officer at Ribbon Communications Cloud and Edge Business Unit, responsible for the technical direction and strategy of product lines worth approximately $500 million worth of business a year. Justin graduated from UWE Bristol on Computing for Real-Time Systems course in 1997, enjoying a career in embedded software development before moving into systems engineering and architecture work. Justin has presented at numerous conferences, published articles in trade journals, contributed to standards work, and has been author or co-author on numerous patents ranging from protocol processing to use of AI and ML in security and networking. So we are delighted to have Justin with us today here. So Justin, I'll hand over to you. Thank you very much.
Thank you, Phil. Thanks for the introduction, and thanks for everyone taking the time to join me today. I'm going to talk a little bit about telecommunications in general, give a little bit of a backdrop as to the state of the industry, what's changing and why some of this is becoming complicated. Then I'll spend the latter half of the presentation going a little bit more deep on some of the AI ML algorithms we use and how we're trying to combat some of those problems. So I'll just do quickly one slide just about Ribbon, just so you got some context about the company I work for and who we are. So we're a global provider for communications infrastructure. So we build the network equipment that helps your telecommunications, internet, mobile traffic, everything like that actually get around the world and connect to different services. That's all I'm going to say about that. I'm going to dive straight into the main presentation now. So first, I want to kind of set the scene with is I want to try to give you some context for how hard networking in this space is and some of the complexities we have to deal with to make global telecommunication systems work across corporate boundaries, country boundaries, global boundaries, and also try to keep all of that secure. So I'm going to start off by just kind of going up the layers of the network and explain some of the key technologies and some of the key things that are involved in this. I'm sure some of you would have come across the OSI 7-layer standard model for networking, and effectively telecommunications follows a very similar pattern. At the very lowest layer, you have the physical transport infrastructure. Often this is optical networking, connecting cities, different data centers, etc., and is really high bandwidth using multiple wavelengths within the light spectrum to provide different services, etc., but is networked across the optical layer. Then above that, you have the more of what you would be familiar with from an IP networking point of view. That layer is on top of that and provides the packet infrastructure on top of the optical networking infrastructure. So this is your lower layers for transporting and then data delivery. At this level, everything is just packets. We're just transporting information around, and these layers are completely agnostic as to what's in those packets. It doesn't know whether that's a Google search query, a voice call like we're on right now, or you're watching Netflix. It's just packet data flowing around the country. Then above that layer, you get into the sort of the application layers from the OSI level model, and in telecommunications that's the same. And in the application layer, this is really where my side of the business focuses on, and what I build is all of the infrastructure that helps you connect to services across that network and helps you to make a phone call, people or visit a web page on your mobile. People do this every day, hundreds, thousands of times a day, but often people don't necessarily pause to think about how that actually happens. How do you actually get that call to go through and find where you're trying to connect to? Or how do you get that web page up on your browser? How does that device connecting to the network securely? How is it authenticated, allowed to access the network? How is it then connected into the network from a routing level? How the packets flow from that device into the network? And then how does the network know what services you're trying to connect to, route those appropriately, and ensure that you're connecting to the right parts of the network you're allowed to? To achieve all this, there's a whole range of different application layer protocols and systems that we layer on top of those transport infrastructure. And this diagram gives you some insight to the types of different capabilities that's at this layer and how they can get quite complicated quite quickly. And I'm not going to go into all the details, and don't worry, we're not going to deep dive on all the details here, but I just want to give you a sense that as you go up the layers of the stack, it quickly starts to get quite complicated. There's a lot of stuff going on that we need to be aware of from our point of view, from the network securing point of view.
You know, to learn more, but it's you, right?
I don't know whether that was a question or somebody just off mute. I'll carry on, but if you have any questions, please feel free to contact Phil, John, or Ian or myself, and we'll deal with it. So just giving you that high-level overview of some of the complexity of the network. Now we're going to talk about the fact that, okay, we spent decades building networks that way. Now things are starting to change. There's a lot of things going on within this infrastructure that's making it even more complex and challenging from a security point of view. The first thing that I'm going to touch on is the fact that telecommunications and data networking in general has historically relied on physical security. There's been a lot of segregation based on physical premises, things being secured in a particular location, physical hardware being dedicated to a particular function, often proprietary hardware that's custom built and so difficult to get the specs on or interface with in other ways, and with custom hardware, custom software running on that hardware. And in part that was driven by security, but also it was more often driven by performance. These systems have to deal with millions and billions of packets and flows, you know, in any given window. And so being able to process that information in and out of the systems at high speed and low latency, it often required hardware assist. However, Moore's law is really caught up with where we need it to be to make more and more of that virtualized as pure software. In addition to that, virtualization as a technology has really improved in terms of how it gives you better access to the hardware. If you think about technologies like SRIOV or DPDK, you can now have applications that historically would have been difficult to build in a virtualized environment, accessing the network interfaces and the lower layers of the hardware, and even doing GPU optimization, things like that, in a way that allows you to really get performant applications on a virtualized infrastructure. So we've seen a shift from hardware, custom hardware on a premise, to software now just being a VM in a cloud. So, you know, this diagram shows how we used to build racks of hardware. Now you can literally go to AWS, click on a link and download and run a network function as part of a telecommunications infrastructure as a VM in AWS. You can do the same in Google and others. And that has implications for how do we secure that, right? You're now running in shared public infrastructure, whereas previously you were running in dedicated hardware infrastructure. You also are more elastic. You're now able to turn up functions and turn them down more quickly and easily than you could historically. So as networks grow, historically that was a truck that needed to be delivering hardware somewhere. Now we can just turn up additional VMs, which means that it's a more challenging environment to keep track of the nature of the network and exactly what's going on within it. And we'll come back to some of these themes as we get into the later sections of the deck as well. Another thing that's really changed is that historically telecommunications and data networking was a very closed software industry, and everything was built by vertically integrated companies that built the hardware, they built the software, and you built a complete solution from a vendor. These days, that's not really the way it works. These days, increasingly open source is used for many functions, both from the point of view of libraries and systems that we integrate into the software to make the software more agile, quicker to develop, quicker to market, but also in sometimes actual whole modules or whole systems are built as open source and delivered as open source, which is fantastic from an efficiency, a time to market, an ability for the customers to get software delivered to them with updates more quickly. But it has its own challenges in the sense that now it's harder to be completely certain what's in the software. It's harder to know for definite that the software you're pulling in from a repository has met the same security standards as what you would have done historically. And you know, SolarWinds supply chain attack was a great example of where this was a risk, right? You know, the fact that it was no longer absolutely certain what software was getting into a continuous integration, continuous delivery pipeline meant that suddenly many more enterprises and customers were potentially put at risk from the software they were putting into their environments. In a telecommunications environment, that's particularly problematic because now you don't know whether that system is secure as it was previously. So the industry is grappling with how do we make the best use of open source software and open source environments, but at the same time ensure that they're secure. So another big change is the technology itself is evolving. So we've spoken a little bit about how the environment we're operating in, from hardware to virtualization, from closed software to open software, is changing. But also, we're actually, each generation of mobility is adding new capabilities. And most people would be familiar with 4G or LTE devices today. That's the predominant network that we use for much of the world. And would no doubt heard of some of the stories around 5G coming into the environment in the near future. What does 5G really do for us? What does it bring to the table? What is it that is providing that the previous generation didn't provide? So I'm going to talk a little bit about that now. So 5G is providing increased bandwidth, increased spectrum, and different types of spectrum that you can use. And so there is the very natural evolution from, I have a device today that can do a certain amount of bits per second, or megabits per second, whatever you want to measure it by. Going forward, that will be able to do many more. And in fact, it gets to the point where those devices can legitimately start to compete with home broadband speeds on a regular basis and give us enhanced mobile broadband, which is the ability to provide broadband over a mobile device more effectively than we can today, which is really valuable from the point of view of being able to provide last mile coverage for some of the more rural settings, things like that. That in itself is a fairly straightforward change. The more interesting changes, I think, is around the bottom of this pyramid here, the massive to machine type communications and the ultra reliable low latency communications. So what do these mean? So all the way back to sort of GSMA and 3G days, there was this idea that you would want to be able to have the mobile network allowing you to connect to physical systems within the environment. So early vending machines, for example, would sometimes have a GSMA or 3G modem embedded within them to allow them to dial home and say, I'm out of Coke or whatever it was, and get a delivery truck roll to update the machine with more stock. During the 4G era, we got familiar with the idea of IoT. We've all started to get familiar with the idea of smart homes, smart bulbs, door sensors, whatever it is. 5G kind of acknowledged that as a trend, and one of the things that it's really resolving to fix within the 5G era is the amount of devices that you can have within a footprint. At the moment, one of the limitations around 4G is just the sheer number of devices you can fit within a particular cell area and how many of those can register simultaneously through a particular access medium. For mobile phones, that isn't such a problem. But when you then have 10 devices per person or 100 devices in a house, suddenly those orders of magnitude start to roll up. And so one of the things that 5G is really fixing is the idea that you want to be able to support millions of devices in a square kilometer and be able to have many more devices connecting into the network, which means your network is now suddenly much more porous. You've got many more devices connecting into the network. You couple that with the fact that eSIMs, the ability to have an embedded SIM card, is coming out in the same era, and you no longer need a physical SIM, and suddenly devices can be produced en masse with built-in software, built-in radio connected to a network, and you don't necessarily know the history of that device or where it's come from. It's harder to secure those devices. So this is another area which provides security issues for the network. As we look at IoT, smart cities, and the evolution of sort of the industrial 4.0 mindset within our wider economy, one of the other use cases that comes to the forefront is the idea that we can do control loops with this sort of networking. So what do I mean by that? Well, from a control loop point of view, what I mean is the ability for a sensor to detect something's happened, communicate that to the network, have a service within the network, then tell some action to happen where that sensor is. So a typical example might be fly-by-wire or automated driving systems, or traffic control systems, or train systems, things like this. Unfortunately, one of the things you need to be mindful of on this is the latency has to be considered. If it takes you too long for that signal to reach a control point, that control point to compute something and then send back a a response to enforce an action, it's going to result in crashes and deaths. So we have this new system within 5G called ultra reliable low latency communications, which is certain bandwidths and waveforms within the 5G spectrum set aside for providing extremely low latency communications between the radio and the device, which unlocks the ability for these 5G systems to really start supporting many more distributed control systems, where the control systems are in the cloud, but the actual thing that's physically doing something can be within the environment. The final big change within 5G that I want to touch on is over on the right here, which is the idea of network slicing. And I bring this up because this is actually already being attacked. There's already research around this in terms of finding security holes in this and finding ways to abuse the policy systems there. Network slicing is really the concept as introduced with the 5G infrastructure of network virtualization, and allowing you to extend the concept of virtualizing a data center or software in the core all the way through the network to the access point, and allowing you to have dedicated sub networks over the internet or the 5G infrastructure that's dedicated to a particular purpose. So you might have, for example, a highly mission critical IoT slice for self-driving cars, which corresponds to an ultra reliable low latency communications radio path, but in the core of the network has dedicated bandwidth, dedicated service characteristics to ensure that that's carried all the way through to the data center. And part of the introduction of network slicing is that segregation and the ability to allow that to happen. But in order to make that happen, there are certain updates to the network, certain things that are happening within the network to enable that. And if you go through this paper, people are already starting to poke at that from a security point of view and find flaws and ways to attack that. So again, just some indications of some of the issues we're grappling with as we try to secure these highly sensitive networks. I just want to reiterate on this point here. So I touched on the previous slide the idea of ultra reliable low latency communications and the need to be able to deal with very fast response times at the edge of the network. And this is tied into something called edge compute or multi-access edge compute NEC. And it's this concept that clouds today, when we talk about an AWS cloud or Google cloud or something like that, are highly centralized with a number of data centers, but essentially you're reasonably remote from where that application's running. As we move into the 5G era, what you'll see, and if you look at the industry views around this, is that those clouds are also becoming more dispersed and moving closer to the edge. You're having miniature instances of AWS or Google or Azure, any of them, popping up within the data aggregation centers for telecommunications infrastructure at these different points towards the edge, whether that's within the regional centers, the edge infrastructures, all the way out of the enterprise space. But you may ask, why is that important? Why would you want to do that? Well, it allows you to run applications at a point where the physical connectivity from the application to device is much shorter, which means that your latency and your time to deliver that communication is much shorter. And so you have this trade-off. In the central core area of the network, you've got high availability of CPU and power, compute, availability of space, but it takes you longer to have that communication from the device to the core of the network. Whereas at the edge of the network, you've got much more constrained CPU, power availability, but you've got a much higher, a much lower latency. And so you can get much better connectivity and quicker services to the edge of the network. So there's this problem at the moment where the industry is trying to work out the best places to run applications. And what we're actually seeing is that applications are becoming mobile, and applications may be running near the edge in some circumstances and may be running in the core at other circumstances. So that further complicates the security posture and the security view of the network, because now you're not even sure whereabouts in the network those applications that people are trying to necessarily attack are actually going to be executing, and what's the security that you need to put around that. And this all leads me to a key point here, which you would have seen in the press, I'm sure, that pretty much every global power has some kind of security posture around 5G. And I've got some of the links here on the page, which I'd encourage you to go take a look at. But the EU, the US, UK, all of the powers that you'd be monitoring has come out with a set of guidelines, security standards, and applications that need to be considered when you deploy a 5G infrastructure to ensure that this critical national infrastructure isn't exposed to additional attack vectors, and the new services that are being delivered by it are actually secured and ensured that we don't end up with a situation where somebody's hacking your smart car and making you crash. That's really what it comes down to. At the end of the day, this is life and death stuff. We need to make sure that these services are able to be delivered successfully, reliably, and securely. Right. Having kind of spent the first 20 minutes or so going over like a whistle-stop tour of telecommunications, the landscape, and kind of the stuff that's changing within the landscape at the moment, to give you some sense of the complexities we're grappling with, I'm going to shift gears slightly now and give you some examples about how do we actually solve some of this, and what are we doing to help fix some of the issues here. So, and the key thing to focus on, and I'll get into the details of how we use this, is really at the same time as this is happening within the industry, big data, ML, and artificial intelligence is really kind of stepped forward in terms of capability. And it's really coming to our rescue. It's given us the ability to really understand these networks in a way that we couldn't previously at a time when it's most critical. So it's really helping us to solve some of these issues. And I'll walk you through now how we're doing some of that. So just to recap the sort of problem statement we've been through, right? How do we know who's doing what on the network? You can do port scanning and stuff like that, and we do that. That's part of the process. But networks are no longer static. They're expanding and contracting on demand. VMs are being deployed and torn down as needed. So you no longer know exactly what the topology of your network is, or exactly what the capacity is. They're becoming more autonomous in that way. The networks themselves are increasingly using public and shared infrastructure, which makes it harder to have confidence over physical isolation and security, which was one of the cornerpins of securing these kind of environments historically. Software is no longer closed or from a single source, which opens up more surface area for backdoors and attacks. And we've seen examples of that. And in fact, there's been some studies. There was an example recently where one university in the US was experimenting with forcibly putting in malicious code into open source, got caught, and the entire university got banned from doing that. But it was a study just to see how easy it was to get malicious code into open source, and they proved that they could do it. Software this is something I didn't touch on particularly earlier, but software is no longer staged and tested separately. What I mean by this is that historically, when we upgraded networks in the past, we would have a dedicated lab to one side where that software was staged, tested, and deployed for a period of time in isolation to verify that everything was working as intended and there wasn't no unexpected circumstances appearing there. With the push towards continuing integration and continuous development from the web side of the world sort of permeating across this space as well, there's really a desire by companies to get into a more agile way of doing software development and deployment, with quicker deployment of software into the network, which makes it more cumbersome and more difficult to know exactly how that software is being deployed, what it is doing, and whether there's any issues with it. So it requires more maintenance. I touched on eSIMs and the fact that physical SIM cards are no longer mandatory, and physical SIM cards are a great security device. At the end of the day, if you haven't got a physical SIM, you can't connect a device to a 3G or 4G network, and those physical security SIMs are production controlled and issued through authorities that are tracked, and we have a way of knowing that a device is approved. That is no longer going to be the way forward for eSIMs. There's security certification and things like that happening around it, but it's not the same level of security. There's orders of more magnitude of devices connecting into these networks. How do you audit and verify the integrity of all those devices? That's next to impossible. And the systems themselves are being expected to be supporting ever more safety critical infrastructure. So against this backdrop, we need to really solve these problems. Which brings me to one of the solutions I work on in particular, which is our the Ribbon's Analytics portfolio. And this is a solution that we build to surface data from the trillions of records that these networks churn out, try to then extract the information that allows us to identify whether there's an issue in the network or a security problem in the network, and then work out how do we actually do some mitigation around that. In this central column here of the diagram, where it says about the real-time software-based big data platform, under the hood of that diagram, this is actually a massive Hadoop distributed database running a data ingest pipeline that takes data from all the nodes within the network, filters it, extracts relevant information, and stores it into the Hadoop system using a Kafka bus to distribute the data across the different elements. And laying on top of that is a whole bunch of analytics applications and sort of TensorFlow-based ML and AI workloads that we run to look at that data and then decide how to infer some conclusion from it. And that's really what I'm going to be getting into in the next part of the deck. So at a first level, we use machine learning to automate much of what we've just been discussing on this call so far. We use machine learning to deal with orchestrating network events, working out whether there's a congestion point and then therefore determine we need to apply more resources, spin up more instances of software. We use it for looking at the network to see whether there's any issues around call drops or devices that are failing to register. And we can use the deep logging that we have within the network to look at the most probable causes of that and then reach a sorted, prioritized list of things to go take a look at to how to go fix that. We do care, marketing, and monetization for the customer as well, helping them to understand what they're getting out of the experience, making sure that the carrier is able to ensure the customer is happy. And all of these functions use fairly simple algorithms. Most of these level functions you can do with simple classifiers. You can do k-means clustering, random forest decision trees, things like this to surface a lot of this data. There's more complicated things we need to deal with though, and I'm going to do a deeper dive on one of the more complicated ones to give you some insights into some of the stuff that gets really kind of gnarly quite quickly. So just to kind of set the scene for some of the deeper case that I'm going to go into, as I've explained earlier in the deck, we've got less confidence that we really know what's going on within the network. The networks and devices are scaling now to a feasibly large number for humans to keep track of, right? It's impossible for humans to just keep an eye on everything that's going on within the network. We are lucky though, there is a lot of data. These networks are extremely data noisy. Every one of these nodes within the network is generating thousands and thousands of events, continuously, millions of events. And all of that data is stored into data files and logs. Where we're unlucky is it's really a non-trivial problem to extract really useful correlated data from that wealth of information that's coming from the network and try to use that to identify expected flows of data on the network versus anonymous flows. And really that's what you want to do. You want to know this set of data that's flowing across the network is behaving as expected and therefore it's okay data. This other flow is doing something anomalous. It's something that we don't think it should be doing. It's either going somewhere it shouldn't be, it's using a bandwidth level it shouldn't be, or it's perhaps using a type of service it shouldn't be using, or it's kind of a device it shouldn't be. Those are really things we're trying to surface in this. And a good way to kind of think about this is this data that we're trying to extract useful information from is kind of comparable in at a loose sense with the sort of problems you have with natural language processing or object detection in a picture. You know that there's a lot of information there, and you know that the information you want is there somewhere in that material you're looking at, the corpus of data you're looking at. But how do you actually extract that? That's a hard problem to automate. And the industry has been struggling to do that in object detection and NLP for decades. Recently, we've had great strides because we finally hit the point where the CPU power, particularly when you get into optimized AI like through GPUs or TPUs, plus the data footprint we can access is that much larger that actually then starts to solve the problem. And it's the same situation for us on the telecommunication side. It's a very similar problem statement. So what we want to try to do is we want to try to get an AI system that allows us to extract the useful signature data from the network to understand what it is that's going on, and that's really the problem statement we were trying to do. There's a bunch of patents that we filed around this, and there's a link there to the core body patent if you want to go and find more information about how that actually happens under the hood. And you can look at the maths and some of the more complicated details in there if this is something you're interested in. In order to kind of frame up the problem a little bit further, I want to just give you a really quick, brief insight into one of the key protocols that runs on these networks. This is a protocol called SIP, Session Initiation Protocol. It's loosely based on HTTP. It's a text-based protocol, similar kind of concept, but it's way more complicated at this point. This has been extended and extended and extended for decades, and now has probably north of 400 RFCs listed at the IETF that cover aspects of this protocol. And so that's part of the challenge. It's just an incredibly complicated, very rich protocol. Another part of the problem is that the protocol itself is very loosely defined, in the sense that the idea is that you should be strict in what you send, but loose in what you receive or interpret. So the idea being, in order to improve interoperability and make sure systems can talk to each other, we should be pretty restrictive in terms of adhering to the guidelines when we send stuff, but when we receive stuff, we should be pretty generous at allowing ambiguity in the receiving message. So, we smooth over some of those issues between the receiver and sender, which unfortunately allows a lot of diversity in how messages can be put together, the content of the messages. I've got a sample here on the diagram of one message on the right here, but in real world instances, these messages can be dozens or hundreds of lines long, with many different pieces of data included in them. And they can be done in arbitrary orders and all sorts of different things, which makes it a very complicated system to autonomously extract information from. So how do we go about solving some of this? How do we take all that data that's within the network and find a way to extract something useful for it? So after a bunch of research, where we settled on was we implemented something called an autoencoder. For anyone who's not familiar with the term, an autoencoder is kind of like two back-to-back deep neural nets. And the idea is, what you're trying to do is you're trying to take a set of features from the input data, compress that into a smaller set of features, which are representative of the most important aspects of the original data, in such a way that that smaller set of features can then be used to reconstruct a close proximity of the original data. So another way of thinking about it is kind of like a feature compression algorithm. You take a very large set of data, you automate the process of picking out the most important pieces of that data that allows you to have a decent stab at reconstructing the final, reproducing the original version of it. To use the image detection analogy that I touched on earlier, another way to kind of think about this is kind of the difference between looking at a bitmap image and a vector diagram. A bitmap image has all of the information there, but a vector diagram just tells you the key things you need to reconstruct that diagram, whether it's a circle or square or a set of things. And it's kind of been pulled out and extracted. And then if you follow the instructions for that vector diagram, you can reproduce the image again. You can create the original image. And that's a similar problem statement to what we had. So what we do is we use a back-to-back encoder, decoder, autoencoder to train the data and verify that as we're inputting the data on the left-hand side, having selected a set of features we think are appropriate, that data is compressed into the really important features that we really want to look at, and then we re-decode that to verify that the final version is similar to the original. So what you're looking to do here is you're looking to have a set of deep neural nets that are trained such that the left-hand side and the right-hand side are relatively similar. So you're looking to minimize the loss between the right-hand side and the left-hand side. So when you look at the maths behind this, that's really what it's trying to do. Once we've done that, once we train that, we can then use just the encoder side as that compression function. We can take that to look at a very large set of data, so x1 through to xn, a very large set of input parameters, and we can use that to compress to a set of much smaller output signature numbers, s1 through n, which allows us to really, what that's doing for us is it's calling out what was the most important attributes in this data that came in, And therefore, that's the stuff we can focus on doing classification on to understand how do we surface problems and issues within the network. So yeah, a more visual example. This is focusing in on a small number of vectors to make it a three-dimensional diagram, but understanding the math behind this, that you can have arbitrary number of vectors is just really hard to visualize a 4D or 5D or 6D drawing. So we just simplify it down for this sake. What we're doing here is we're using that encoder we just did to look at a large set of data, and it basically learns from that data what devices are connected to the network, and it can do that by clustering similar sets of signatures, similar sets of key data that is surfaced from the encoding phase. And this allows us to create these visual diagrams where the different color sectors is telling us the families of devices that we're detecting on the network and whether those devices are ones we would expect or not. I just seen somebody put a hand up on a question here. Do we want to just take that a moment?
Andy, do you want to come off mute and ask a question?
No, never mind. We'll carry on. We hope we have some time at the end to do some more questions as well. And here's another version of the same thing. So this one is looking at end users. So the previous one was clustering around devices. This one's clustering around users and trying to identify sets of flows or sets of call events or session events related to a particular user. So we can start to track over time whether a particular user is using the network in a particular way, and then we can cluster that into sets that we can then start to aggregate into buckets and start to look at trends across the network. Where this gets interesting is if you then combine the two together, we can then start to think about fraud events and security events. You can then start to say, okay, I've got a set of signatures that tells me what devices are known in the network. And I've got a set of signatures that tells me what users are known in the network, and I've got a normal distribution where that shows how they correlate. If I then suddenly look at a pairing that is no longer making sense, no longer correlating because it's flagging up like in the right-hand diagram here, that's an anomalous event. That's now telling me that user is doing something it wouldn't normally do with that device, or that device is being used by a different user that wouldn't normally be using it. And that tells me something interesting about what's happening with the network, perhaps indicates a fraud case or a change in usage or something that needs to be reacted to. And if you extract that out across all of the things we're doing in the network, this is kind of fundamental tools we use to really understand whether the network and the traffic on it is behaving the way it's really supposed to. So I wanted to just spend the last couple of minutes here that I've got on the deck, just to give you some sort of real world examples of what does that mean. So, using those kind of tools, we can start to provide customer care use cases. We can start to understand whether a user is using the device in the way that they're supposed. Not supposed to is the wrong word. In a device that's nominal for them, the normal way they use the device, or whether there's something anomalous going on for them. We can also look at whether calls or sessions are being dropped or there's problems within the networks. And we can also look to see whether there's an issue with the network that's causing an issue on our network, right? There might be some crash on the network caused by something, and we can look at what was causing that. And at the time, we might have found, for example, there's a new device signature. So perhaps that device has got some problem that's causing an issue on the network, and we can look to ban those devices or scrub them from the subscriber database. We can also look at security on the network. For example, we can look at spam calling across the network, which is a big problem at the moment, and it's actually becoming legislated for in the North America. We can look at, say, is this set of numbers making a calling pattern that indicates they're likely doing spam calls or fraudulent calls, and therefore we can flag those, add them to a list, and start to blacklist them, things like that. We could also do telephony dial service detection. So telephony dial service detection is often telephony denial of service is often accidental. You know, anyone who tried to ever get Glastonbury tickets or tried to, vote for X Factor or maybe try to get a COVID vaccination would have gone through some of this. You know, there's these events where something opens up and suddenly it creates a surge of inputs where everyone's trying to do the same thing at the same time, and often that can take systems down, and identifying those peaks and surges allows us to react. Remember I said earlier on that the networks are getting more elastic. What you can then do is you can see, we've got a peak appearing, we can turn up more capacity, we can add more nodes to the network to make the elastic network expand to fit the new demand. And then finally we can look at fraud behavior. You know, is this pattern of behavior consistent with what we'd expect for this type of user class or this type of network device? I'm going to go a little bit deeper on this particular one because there's some real world use cases I can just cite here. I can't cite company names for obvious customer sensitivity reasons, but here's an example of one customer. So this was a customer on one of our networks, where the carrier notified them that they had a sudden high volume of uncommon international calls that they hadn't had previously. When we kind of looked into that, we actually managed to identify that a Skype conference bridge had been hacked. It looked like it was a legitimate direct dial number for that Skype number, but was somehow being abused. And it occurred over a number of months. They actually ended up, the company ended up racking up over $100,000 worth of additional fees to this hack. And what we managed to then do is the initial reaction was just to block that particular number. But what we were able to do by looking at the trends over time, the behavior of the numbers and the events around that, was look at the reoccurrence, and we were able to spot when that number was changed or other events happened that were similar. And we're able to catch a number of different calling party numbers that was trying to do the same thing again and actually stop it ahead of time. So that was a really good, successful example of how using ML and these kind of algorithms can help to really catch issues before they start to become a problem. And another example here was, this was a multinational food manufacturing company, and they had a SIP trunk, which is basically just a name for a very large connection for calls between their center and the network. And we were seeing a very large number of calling number dialing again, and then dialing out to Europe. And over a period of time, this generated 200K's worth of bills for that customer. And when we looked into it again, what we discovered were that the heat map of the abusing numbers and things like that is that this had been penetrated, and basically people were using that trunk to forward to international numbers, and it had been sold as a service on the black market, and people were just basically using this trunk to deliver international calls at the expense of the customer because they'd been able to break into one of their provisioning and actually be able to access the system. So we were able to identify that, and then we were able to kind of keep track of heat map of calling party numbers around that and the interval times that were involved in it, and identify the anomalous traffic from the legitimate traffic and help them kind of get that under control and scrub that from their system before eventually reprovisioning and fixing the problem. And so with that, that's kind of the end of my deck I was going to walk through. I wanted to just give you some insights into some of the problems we're facing and some of the ways we're trying to solve it. And I've got a few minutes left, Phil and team, if there's any questions or anything else you want to talk about.
Excellent. Thank you very much, Justin. It was really interesting. So if there are questions from anyone who's on the call today, please do feel free to use the chat or put your hand up, raise your hand, and we've got some time for questions. So I suppose if I may start, just whilst we're waiting for people who might be typing. Sure. It was really interesting to hear the level of machine learning being used to essentially, you've got a large amount of data. How do you filter that and manage that data? So it was really interesting to see the extent that machine learning is being used, and in particular, the example you gave around the user and device profiling and how you combine those. I thought that was really interesting. So I'm just interested to know what you see as the biggest challenges going forward in terms of whether it's about how we understand machine learning and how we understand analyzing this kind of data, the reliance we're placing on machine learning algorithms and the like that. But yeah, really, what are the biggest challenges going forward for you in this domain?
Yeah, it's going to sound strange, but it's and maybe something that's a trivial issue. But actually, one of the biggest issues we have is getting network operators to share the data. Right? It's very hard to do training and improve the models if the operators are reluctant to share the data, and they are, because there's very sensitive information in many of these systems, particularly now we're living in a time of GDPR. We can only make the AI systems as good as we can make as we get access to data. We have been able to foster some good relationships with particular customers who trusted us for a long period of time, and they're starting to give us access to more and more of their data. But we're also doing more what should I say, more thinking outside of the box with that. So we're in the process of actually setting up a honeypot in AWS, where we're setting up a network with many thousands of lines attached to that, and we're not advertising those numbers or doing anything particular with them. We're just leaving them there and monitoring to see who calls them. And that's one way for us to learn about spam numbers, things like that, because they're indiscriminate. They will often just go through a whole range of numbers in an environment and call them. And that's another way for us to collect useful data and aggregate that together with the data we're getting from the networks to really get on top of it. So from my point of view, the biggest challenge is always with this stuff is the data engineering, the data science part of it, and getting access to really good data. And more often than not in our industry, that's more of a political sensitivity than an actual problem that the data doesn't exist. The data's there. It's about getting permission to use it, particularly getting, I guess, just to add to that, particularly getting permission to aggregate data from multiple carriers. That's something that's really sensitive. When you start saying, I want to pull together, the web traffic on AT&T with the web traffic on BT and pull that together to get an aggregated view, then carriers get extremely sensitive.
Excellent. Thank you for that, Justin. The other thing to think about that I wanted to ask, just building on that, because you raised a really important point. Machine learning is all well and good, but it is only as good as the data that you start off. And I wonder whether privacy preservation is something that's coming about in this particular domain. In research, we talk about privacy preserving machine learning, how we can gather information at the edge without revealing sensitive characteristics. So I just wonder whether that's something that in this particular industry is starting to come about.
It is. It's actually really important. I think GDPR really changed the situation a lot with this. Once our customer base really understood what they could and couldn't do from a data sharing point of view, that really changed how they approached it. And in some of these situations, the data we're after is more about network level events and less about individual user level events. And in that situation, it's perfectly fine for us to obfuscate or even remove the user identifiable data, the P2 data. We can work with the carrier to say, this user identifiable information, whether that's an IMSIM or a SIP ID, whatever it is, we can scrub that from the data before you give it to us, and we'll work with them to work out how to do that. And also our analytics system as well is distributed in such a way that where we ingress the data from is distributed down into the network, and we can put filters within that, so that even at the network point, we can start to scrub data and use intelligent algorithms at the edge to say, we know enough about the format of this data to know that these fields need to be ripped out at source and not transmitted to the core, and we'll just send the rest of the stuff up. Oh, one other thing I will say, Phil, as well, is sometimes it's enough just to know there's a correlation. You don't need to know who the actual user is. So sometimes it's okay to effectively one-way encrypt the data and say, long as that hash is going to generate the same encryption for every time it's used for that data, it's perfectly fine to do that as well in some of these cases. All we're really trying to do is just try to see, is this set of data related or not? And sometimes we don't care about who that data actually belongs to. We just want to be able to say this set of data is correlated. And so sometimes we do that as well. We'll keep the fact that the data is uniquely identified, but we'll encrypt it in such a way that we can't reverse that, so that we can then just correlate the data.
Absolutely. And I mean, I thought it was really interesting when you're talking about the use of autoencoders. And as you say, you know, an autoencoder is great for being able to encode and then decode from a compressed signal. But as you said, you know, if you also want to use that as a one-way function, that makes a lot of sense as well. Are there any other questions that anyone would like to ask? We've got a couple of minutes.
I did see one here that says, I contain 3 cloud providers. Do you think we're eventually going towards monopolization? No, I don't. And actually, I think it's getting more diverse. I do think you're going to get a handful of very large whales in this space that really kind of control some of the space, but you're getting more people try to join that as well. So although I focused on Google and AWS as the 2 key ones, we do a lot of work with Microsoft Azure, probably more so in some areas, but we also work with IBM and others. Oracle's another one that's trying to get into this space. So I think that's going to be a diverse space for a while.
Andrew had a question in chat as well. He said, are we at greater risk within the core from Huawei or open source software?
Yeah, I wish I could answer that. That's probably one for GCHQ. I don't have any way to give you a qualitative answer on that. I would say that Huawei's been used for many years perfectly happily within UK networks. You know, some of this, sometimes there is real technical reasons why things change. Sometimes there's practical reasons why some things change. I can say that for on the open source side, most of the time open source is absolutely fine. The only risk really is in your processes and whether your process is robust enough to really understand what you're pulling in, or whether your process is such that you are maybe passing through stuff without really taking the time to understand what's in there.
And I had a question for you, actually. I mean, at the moment, I think we, or you, because I know that you work for Ribbon, kind of assume that the threat actors are kind of dumb to what you're doing with your sort of fraud protection and machine learning models here. Do you see a point in time where you think the threat actors are going to be sophisticated enough and kind of understand what it is you're doing with AI to start performing adversarial attacks on your models and try and thwart you that way?
It's definitely an arms race, and it's definitely like for every time you come up with something which you think you can easily correlate a load of data together, eventually someone's going to find some way to say that they've got a different way of doing that. I think one of the things that's which is to our advantage, is ultimately certainly on the spam side. It's a little bit different on the fraud side, but on the spam side, it's only effective if they can keep the cost per event very low, right? Spam calling only makes sense if it's trivial or not negligible cost per event. Once they start having to do more sophisticated things to rotate through large large number bases, for example, that becomes costly. So there's a certain upper threshold on how sophisticated spam at least can get before it becomes cost effective. Fraud is a different situation, and that definitely is very much an arms race, and there's very real financial reasons why it's in their interest to keep pushing that yet. So that's a constant back and forward and involvement. And I think that's the same with you know, generic security with the desktop or anything like that, right? You know, you see, you know, every year there's a new virus update and the new, you know, signatures are updated all the time. That's just par for course, and so saying we'll experience too.
Thanks for that. Yeah, that was really interesting. I mean, that's the thing. As we rely more and more on machine learning, it's understanding, you know, does machine learning in itself introduce weaknesses?
Yeah.
And again, you know, as you were saying, that point of the cost-benefit analysis, you know, is it actually worth your effort to try and circumvent it for the gain you're going to get? Really, really interesting. Yeah, sorry.
Yeah, I was going to make just two comments on the back of that, Phil. One is there is still a lack of trust with fully automated AI, and we still, for most part, with our customers, use the AI to surface recommendations, and then they make the decision about what they want to do next. You know, in principle, this could be automated. You could close the loop, but that doesn't tend to happen. It tends to be there's still a human in that process. The other one I think is, I didn't touch on today's conversation, but one that I think is really started to become interesting is the use of AI for natural language, natural voice synthesis, and the fact that that changes the landscape around detecting certain classes of spam call, because a lot of the spam call detections today that are static are based on the fact that it's a pre-recorded message, and you can just analyze that waveform is very similar or the same as another waveform. Once you have AI-based speech synthesis, you can then start to say, actually, I'm going to change the script or have variability in the script, which makes it harder. Then you start to have to look at like artifacts of that speech synthesis. So yeah, there's a lot of interesting stuff coming down the pipeline. It's going to make this very interesting space to try to combat.
That's really interesting, actually. That's, you know, that's kind of like your deep fakes for audio, I guess, isn't it?
Yeah.
You know, we know is coming. You know, when you look at the deep fake videos, coupling that with the audio stream as well, and then thinking about that in terms of the telecoms aspect, that's both interesting and terrifying in equal measure.
Yeah, and I think if you look at the Google AI Assist stuff they did recently, where they have the ability to get their phone to call and interact to book a reservation, right? That's a benign or relatively benign use case, depending on how you want to interpret it. But you can see how that technology can be used for much more nefarious means.
Absolutely. Excellent. Right, we are at time. So we will wrap up there. Thank you ever so much, Justin, for being able to join us today. It's been an absolute pleasure and really interesting to hear all about what Ribbon Communications are up to, and especially how ML's being integrated into telecoms now. For those on the call, if you do have any questions and you want to follow up with Justin after this, please email me. I'm sure we can link you up with Justin if there are any follow-up questions. So with that said, thank you ever so much for everyone to join us today, and look forward to seeing you next time.
Thanks, Phil. Thanks, John. Thanks everyone for taking the time to listen.
Cheers. Appreciate your time.